Welcome to another explainer. I am absolutely thrilled you're joining us today because we're going to look at one of the most elegant, honestly mind-expanding concepts in calculus. We're talking about power series, and specifically, we're going to master the generalized binomial theorem. Now, if you thought binomial expansions were just for simple polynomials, well, get ready because we're about to blow the doors completely wide open.
Okay, let's dive right into this. You already know how to expand 1 plus x squared or even 1 plus x to the power of 5. You literally just multiply it out, right? It's straightforward. But what happens when your exponent isn't a neat positive whole number? What if I ask you to expand 1 plus x to the power of 1/2 or to the power of -3? Suddenly, those standard algebraic tools we rely on just hit a brick wall, entirely shattering our usual methods.
Don't worry, though, we've got a highly logical plan to solve this mathematical mystery together. Here's our roadmap for today. First, beyond the classical binomial. Second, deriving the infinite series. Third, calculating complex coefficients. Fourth, the radius of convergence. And finally, putting it into practice.
All right, let's kick things off with part 1, beyond the classical binomial, where we're basically breaking the limits of exponents.
Think about it like this. We're essentially taking a role you learned way back in algebra and literally stretching it to infinity. The stark contrast here is between what we currently know and where we're going. See, the classical binomial theorem requires your exponent k to be an integer greater than or equal to 0, and that gives you a nice, clean, finite sum. It ends. But the generalized binomial theorem, we're going to let k be any real number. And by doing that, our finite sum transforms into a continuous, infinite power series. We're basically trading our comfortable finite world for a completely infinite one.
Moving right along to part 2, deriving the infinite series, using what I like to call the Maclaurin key.
So, to actually unlock these weird fractional and negative exponents, we need a very specific mathematical key, the Maclaurin series. This allows us to build a function directly from its derivatives at 0. Just look at how beautifully these terms build step by step. Step 1, we take our function, 1 plus x to the k, and start finding its derivatives. The k drops down, then k minus 1, then k minus 2, and so on. Step 2, we evaluate all of those at x equals 0. The 1 plus x parts, they just become 1, leaving us with this shrinking product of k terms, k times k minus 1, cascading all the way down. Finally, step 3, Maclaurin tells us to divide that result by n factorial to find our exact coefficient. It's incredibly intuitive algebra when you see it laid out.
So the crucial point here, and really this is the ultimate takeaway of our whole explainer today, is the resulting generalized binomial theorem. 1 plus x to the power of k equals the infinite sum from n equals 0 to infinity of k choose n times x to the power of n. And we define that k choose n exactly as the pattern we just found, that descending product of k terms divided by n factorial. The wild part? This works for any real number k. In fact, if you've ever wondered how your computer or calculator can compute complex roots and fractional powers so instantly without just wildly guessing, well, this infinite series is the literal foundation of how that magic actually happens. Let's jump into part 3, calculating complex coefficients. Welcome to Coefficient Bootcamp.
We've got this powerful new formula, but we need to prove to ourselves that it really works for these wild exponents. Let's take a standard integer first. K is 4, n is 3. The numerator is 4 times 3 times 2 divided by 4 factorial, which is 6, giving us exactly 4. Perfect. Next, let's try a negative exponent. If k is -2 and n is 4, our numerator product gives us 120. Divide by 4 factorial, and our coefficient is 5. We can even do fractions. Check this out. K is 1/3, n is 2. The math holds up flawlessly to give -1/9. But what happens if our n value is actually bigger than a whole number k? Well, if k is 1 and we want the fifth term, our descending product eventually hits 1 minus 1, which is 0. That single 0 cancels the whole shebang out. And that right there is exactly why classical whole number binomials terminate.
All right, part 4, the radius of convergence, or essentially establishing our boundaries.
So we've successfully unleashed these infinite series. But as you know, infinity can be dangerous. We have to establish the safe zones where this math won't just spiral entirely out of control. And this brilliantly illustrates why those boundaries exist. We use the ratio test on consecutive terms of our series.
For case 2, our classical non-negative integers, the series just terminates. It stops entirely. Because it's finite, it converges for all possible values of x. The radius of convergence, r, is infinite. We have complete safety. But for case 1, a general real number, k, like a fraction, the series goes on forever. The ratio test limits us strictly to the absolute value of x. This means our safe zone, our radius of convergence, hits a hard mathematical wall at r equals 1.
Just a super quick side note on what happens exactly on that boundary line right at x equals 1. For non-integer real powers, the series actually diverges. It totally breaks down. But for positive integers, the sum beautifully converges perfectly to 2 to the power of k.
And finally, part 5, putting it into practice. Let's find the radius of convergence for some actual functions.
We're going to test our new knowledge on 4 specific real-world functions to see how we find the radius of convergence for each one. Example A is going to be our baseline, 1 plus x to the power of 5. The general term here uses 5 choose n. Because 5 is a positive integer, the terms eventually just become 0. When we run the ratio test, the limit is 0, which is obviously always less than 1. Therefore, our radius of convergence is infinite. Our baseline is completely 100% safe.
Okay, now things get a little spicy. Example B, 1 minus 2x squared, all to the power of negative 3. Notice the mechanics at play here. Not only do we have a negative exponent, but our x is replaced by negative 2x squared. When we drop that into the ratio test, the math tells us that 2 times the absolute value of x squared must be less than 1. Solving for x, we find our radius of convergence is exactly 1 over the square root of 2.
Example C is where we need a bit of a major aha moment. We have 9 plus x squared to the negative 1/2. Remember, our generalized binomial theorem strictly requires the format 1 plus something. We don't have a 1 here, we have a 9. So we absolutely must factor out that 9 first. Doing so transforms our inner term to 1 plus x squared over 9. Then we plug that new modified x term into our general term, run the ratio test, and find that the absolute value of x squared over 9 must be less than 1. The result? A perfectly clean radius of convergence of 3.
Let's move to example D and see how this all builds together in our final challenge. 1 minus x over 8 to the power of 2/3. We've got a fractional exponent and a fractional x term. We slot negative 1/8 times x into our general term. The ratio test reveals that the absolute value of x over 8 must be less than 1. Multiply both sides by 8, and we get a beautiful radius of convergence of exactly 8.
You know, you have now successfully navigated the generalized binomial theorem. You've literally broken the rules of classical exponents, built infinite power series, and strictly mapped out their boundaries of convergence. That's huge. But I want to leave you with this final, somewhat provocative thought. We've mastered the expansion safely centered at x equals 0. But what wild, unpredictable infinite series are hiding right at the very edges of those convergence intervals? Think about that. Until next time, keep exploring, and thanks so much for joining me for this explainer.